Hello everyone, this video introduces our research work on the robust prior-assisted trajectory generation for benchmarking. We named the proposed method as the PALoc. We come from the Hong Kong University of Science and Technology under the administration of Shen Chen Robotics Institute. Our lab is the Robotics and Multi-Perception Lab, and you are welcome to visit our laboratory website. We have some motivations and challenges for benchmarking. First, we have some limitations of ground truth tracking sensors. For traditional ground truth generation, they rely on various GT tracking sensors, and we may have limited trajectory frequency and incomplete pose degrees of freedom. For instance, we may only have the attitude part without the translation part. And moreover, it may be limited by certain environments, such as the motion capture system coverage. And we also know that GT tracking sensors are easily occluded. And on the other hand, we have some limitations of post-estimation methods. For SLAM methods, we normally have accumulated errors in terms of the growing time. And for map-based methods, we may encounter poor smoothness and robustness in real engineering practices. So for the prior-assisted method we propose in this work, we mainly focus on solving the trajectory generation for benchmarking with good smoothness and robustness while achieving relatively high accuracy. Absolutely, there are some challenges for quantitative evaluation. In engineering, it is difficult to objectively evaluate the generated trajectory. The figures shown in the right present the challenging environments, such as the GNSS-denied cave and the long corridors that may cause LiDAR degradation. Our main contributions are listed as follows. First, we propose a flexible, prior-assisted localization system facilitating the generation of 6-dot dense poses for benchmarking. The second, a degeneracy-aware map factor to address degeneration cases for continuous pose estimation has been studied. And finally, a norm-constrained gravity factor specifically tailored for zero-velocity update scenarios has been proposed. In the right figure, we show the prior RGB point cloud map with the estimated trajectory in red points and the map in blue point cloud by the proposed PALoc method. Let me introduce the first main contribution. We propose a prior-assisted localization system facilitating the generation of 6-dot dense poses for benchmarking. Shown in the right, the figure presents the constructed factograph of the proposed PALoc system. The diagram illustrates the graph structure with diverse nodes and factors. The large gray circle signifies the system state xi, and the smaller color circles denote distinct factors. And for our second contribution, a degeneracy-aware map factor to address degeneration cases for continuous pose estimation has been studied. In this step, we propose an adaptive parameter to tune the factor graph. Shown in the right, the equation stands for the adaptive parameter that we proposed, where the lambda I corresponds to the ith eigenvalue, while EI and VI represent the ith eigenvectors of the measurement and the reference point clouds, respectively. By extending our work with norm-constrained gravity factor specifically tailored for zero-velocity update, namely ZUPT scenarios, we can construct a compact framework of the factor graph, making it adaptive to many static scenarios. We show in the right figure about the details of the norm-constrained factor based on the acceleration vectors measured by the IMU. We also show the direction error terms and the magnitude error terms, as well as the Jacobian matrices. We test our work among many datasets and sensor configurations. The major dataset is the Fusion Portable dataset, which we published in the ICRA 2022. In this dataset, we have many sensors, including an Oster OS1 LiDAR, an STM300 IMU, and a Leica ground truth PALoc laser scanner. The figures shown in this slide depict the basic structure of the device and the robotic systems along with the measured dataset. We conducted various evaluations on the trajectory errors. We have a lot of data sequences on different platforms. We generate higher resolution and high frequency ground truth trajectory, but with relatively small scale. We test many algorithms, including the representative fast LEO2, LEO-SAM, LEO mapping, HD localization, ICP localization, and fast LEO localization. It has been shown that the proposed method is flexible and it can integrate with different odometry, such as the results shown in the table. We use the LEO-SAM as the front end and the fast LEO2 as the front end as well. In this table, we summarize the trajectory errors for different datasets and different methods. We categorize these methods into SLAM-based methods, map-based methods, and prior assisted method we proposed in this paper. The results reflected that for many methods, they may fail in some challenging datasets, such as the MCR normal dataset. And our proposed method maintains both the robustness and accuracy. We also have some other evaluations on the map generation. In these data sequences, only prior map with 6 mm accuracy has been studied. There is no ground truth trajectory, so we can only evaluate the map accuracy and completeness. We also choose the representative candidates from the last comparison. And in the table, we show the results of these representative candidates along with the proposed method. We show a combined solution by the proposed method and the fast LEO2. The final result indicates that the proposed backend improves the accuracy and the completeness of the reconstructed map. We further visualize the evaluated map in these figures. We may see in many challenging datasets, we can still build high-quality maps. We have a demo for the degeneration cases using a handheld device. In this dataset, a corridor-based scene has been studied, and it has degenerated direction in the x-axis, and it has large drift in the z-axis. We also tested the proposed method in an escalator demo. We mainly show the performance of the proposed method encountering the escalator scene with large z-axis change. The next demo is about the partially outdoor scene. We show some scenarios with in and outdoor movement, and in these videos, we may clearly see that the proposed method enhances both the localization and map generation accuracy and robustness. The proposed method has also been deployed on a quadruped robot. We have the motion capture ground truth trajectory with 1 cm accuracy and 120 Hz. The quadruped robot navigates and stops randomly with ZUPT-related factor in the factor graph. Our proposed method has been open-sourced. The practitioners are welcome to download our code and test.